Let's kick off this explainer with a massive question. How do the heaviest machines we ever build manage to completely defy gravity? I mean, really think about it for a second. We're talking about thousands of tons of steel just effortlessly floating on water, or these massive metal cylinders carrying hundreds of people, hurtling through the sky. Seriously, how is this not magic?
Well, let's dive right into it. The exact same physics rules that allow a massive airplane to accelerate down the runway and generate lift, they're the same rules that govern the car you drive, the sports you play, and even the blood pumping through your veins right this very second. It all comes down to understanding the invisible forces interacting around us all the time.
So welcome to the explainer. Today we're going to demystify the complex physics of motion, energy, and fluids. We're going to look directly at the source material to prove that physics isn't just some set of abstract equations on a chalkboard. It's the literal operating code of our reality, written in a universal language of fundamental units and dimensions.
Here's our roadmap for today. We'll start with everyday physics, cover work and efficiency, compare conservative and non-conservative forces, and then we'll dive right into fluid mechanics, terminal velocity, and the dynamics of fluid flow.
All right, Section 1, Physics in Everyday Life, the operating code of reality.
Moving on to Section 2, Work, Energy, and Efficiency, or as I like to call it, the cost of motion.
To really understand this cost of motion, we measure work and energy using a derived unit we call joules. Now, the pro of using derived units like joules is that they're fantastic for quick, everyday communication. But the con is that they can hide the underlying mechanics. When we break joules down into their base dimensions, kilograms, meters squared, and seconds squared, it shows us exactly how mass, distance, and time are actually interacting. Now, an ideal machine would transfer 100% of those joules into pure motion. But just look at the table we're looking at here. An automobile engine is remarkably inefficient. Only about 25% of its potential energy actually does useful work. The other 75%, it's entirely wasted as heat. And that incandescent light bulb down at the bottom, a staggering 5% efficiency. Crazy, right?
Let's hit Section 3, Conservative and Non-Conservative Forces.
So, where exactly does all that wasted energy go? Well, it completely depends on the force field. The physical dimensions of the energy remain exactly the same, but the path you take dictates how much is lost. Think of a conservative field, like gravity. The work done moving an object there is totally independent of the path taken. A round trip nets zero work. Simple. But non-conservative fields? Things like friction and air resistance, those are the real-world thieves. Here, work absolutely depends on the path. Literally, the longer the path, the more energy is actively stolen and just dissipated away from your machine.
Which brings us to Section 4, Fluid Mechanics and Buoyancy. We're shifting over to liquids and gases now.
You see, those exact same rules of energy and resistance apply perfectly in water and air. Archimedes realized way back when that there's an upward buoyant force on literally any object immersed in a fluid. Force is measured in newtons, which, if we break it down into base dimensions again, is mass times length divided by time squared. The sheer beauty of Archimedes' math is that this upward force exactly equals the weight of the fluid that gets displaced. So, by displacing a massive volume of water, a ship's hull generates enough newtons of upward thrust to effortlessly support thousands of tons of solid steel.
Moving right into Section 5, Viscosity and Terminal Velocity.
But fluids don't just lift things, they push back. They do this through a property called viscosity, which is essentially a fluid's internal friction. When objects move through viscous fluids, they experience a retarding drag force. And because drag is a non-conservative force, it steals kinetic energy, and that theft scales up rapidly as speed increases. Just notice how perfectly nature adapts to this. Geese fly in a V formation specifically to cut through aerodynamic drag, which drastically reduces the energy each bird consumes on those brutal long migrations.
Let's look at a human example and see how this plays out for a skydiver in 5 distinct steps. So, step 1, a paratrooper jumps out of a plane. They initially accelerate downwards thanks to the conservative force of gravity. But step 2, as their velocity increases, the upward, non-conservative drag force from the air increases right along with it. Step 3, eventually, that upward drag force perfectly equals the downward weight of the paratrooper. At this exact point, the net force becomes zero, acceleration stops completely, and they fall at a constant maximum speed. We call this terminal velocity. Then step 4, they open their parachute. This provides a massive new surface area, creating a huge spike in drag force that causes rapid deceleration. And finally, step 5, a new, much lower steady speed is reached for a safe landing. Mapping this out visually, you can actually see the paratrooper accelerating to a pretty deadly terminal velocity of 50 meters per second. But right there, at 42 seconds, the parachute opens. The sudden spike in surface area creates massive drag, and it instantly drops that velocity down to a safe, super manageable 8 meters per second so they can have a smooth landing.
And our final section, Section 6, Dynamics of Fluid Flow.
Now, when fluids are in motion, their behavior shifts dramatically based on speed. At lower velocities, we see steady, streamlined flow. Essentially, every particle follows the exact smooth path of the one before it. But push that fluid past a critical speed, and it erupts into this irregular, whirlpool-like chaos known as turbulent flow. As you can imagine, this is incredibly complex to mathematically model. To make sense of that steady flow, physicists use what's called the equation of continuity. It basically states that for an incompressible fluid in a pipe, the cross-sectional area multiplied by its velocity is completely constant. Let's look at the actual dimensions for a second. Area is length squared, and velocity is length over time. Multiply them together, and you get length cubed over time, which is just volume flow rate. So if you decrease the area, like putting your thumb over the end of a garden hose, the velocity of the fluid absolutely must increase proportionally. It has to pump out the exact same volume of water every single second.
And what's wild is that this brilliant equation scales down perfectly to your very own body. In a normal adult, blood speeds out of the aorta at about 0.33 meters per second, but the aorta branches out into billions of tiny capillaries. Because the total combined cross-sectional area of all those tiny vessels is so much greater than the aorta alone, the blood flow radically slows down to an incredibly sluggish 0.044 meters per second. But listen, this isn't a flaw, it's an absolutely spectacular feature. This slow speed is perfectly timed by nature to allow for the vital exchange of life-saving oxygen and gases inside your body.
Ultimately, all of this fluid dynamics stuff ties right back to the conservation of energy. Back in 1738, Daniel Bernoulli mapped this all out. He showed how pressure, which we measure in derived units called pascals, alongside kinetic energy and potential energy are completely intrinsically linked. Basically, if a fluid's speed increases, its internal pressure must decrease to keep the total energy constant. It is literally the ultimate balancing act of energy and motion.
So as we wrap up today's explainer, I want to leave you with this thought. Physics isn't just dry equations locked away in some dusty textbook. It's the invisible, elegant machinery of our entire universe. From the non-conservative forces draining your car's fuel efficiency to the equation of continuity perfectly regulating your own heartbeat. These rules are always playing out right around you, just waiting to be understood. The next time you see a plane fly or feel your own pulse, ask yourself, what other unseen physical forces are secretly shaping the reality around you? Keep questioning, keep learning, and I'll catch you in the next explainer.